In this lecture, we're going to talk about the process of model or variable selection in the context of linear regression models. So the goal of variable selection is to find the best subset of predictors to use in our regression model and to do so in an objective way. Of course, we can choose a set of regressors simply because we think they're going to be good, but we want to have a formal objective process for deciding which variables should be included in our regression model. And in general, we have something known as the principle of parsimony, which is that we want the simplest model that adequately explains the data. If a model is too simple, it may not capture the complex behavior of the data set. If it's too complex, then we may be overfitting the data and trying to fit the observed data too close, meaning that we won't be able to make accurate predictions for new observations. Additionally, if we have unnecessary regressors in our model, then we're actually wasting the information that we have, because we have to use that information to estimate the regression coefficients in our model. And so if we have too many regressors in our regression model, then we have to use some of that information to estimate regressors we have to use that information to estimate regression coefficients for regressors that shouldn't be in the model. And by simplifying our model, we can actually sometimes get smaller models that have more precise estimates and better predictions than more complex models. So when I had mentioned the term overfitting, some of you guys may not have understood what I mean by that, and so I want to draw a quick picture. So let's say that we have data that looks something like this, so sort of like a sinusoidal kind of curve. Well, we haven't really talked too much about how to fit a model like this in our class, so that's okay. But there's different things you can do. You can have a spline model, you can have a model that has sines and cosines in it. But it seems like if we fit a model that had some sine and cosine terms and went something like that through the observed data, that seems like it would actually be a pretty decent fit. But what you can actually do is by adding additional regressors into your model, you can fit the observed data more and more closely. So if we added additional regressors in our model, so for the same data set, or imagine this is the same data set, we can get a model that does something like this. And it's perfectly matching the points in our data set. And you might think to yourself, oh, that's a great model because there's absolutely no prediction error in our observed data set. The problem is that we don't really think this represents the true behavior of our data set, which we think is something like this. And when we write out a regression model, we oftentimes write it out as something like this. So y equals x beta plus epsilon. And this is the mean part of our data set, the structural part, and this is our error. And so what we imagine in regression is that there's some sort of overarching pattern to our data set, a mean structure, that we can typically follow, and then the individual observations are going to deviate from that. And sometimes what happens is if you add too many regressors to your model, you're actually not trying to estimate the mean structure, you really are starting to estimate the error structure in more detail than you really should be doing. And so we don't want to do that. And so we want these objective processes for identifying which variables should be included in our regression model. One of the things to think about, though, as you're doing variable selection is that outliers and influential observations can dramatically impact which model you conclude is the optimal choice among the various possibilities that you're considering. So just like an influential observation can dramatically affect an estimated coefficient when you're fitting your regression model, the same thing can happen when you're doing model selection, just because the individual fits are going to be used in your model selection procedure. So if there are outliers or influential observations, you might consider what model you would get if you remove those observations only in the model selection process. So I've repeatedly emphasized in our class that you shouldn't just remove an observation simply because it's inconvenient. But for the model selection procedure, you might consider the results you would get when the observation is included and also when you remove that observation. Similarly, if you transform your response or your predictors to obtain regressors, then you can get dramatically different results in your model selection process. And so oftentimes what happens is that you might go through an initial model selection process, you identify a few different models to consider in more detail, then you go look at your regression diagnostics and you see that some of the assumptions are violated, which means you need to transform the response or transform one or more predictors. Well, after you do those transformations, it's actually a good idea to repeat the model selection process to see if you get a different model to consider for your subsequent analysis. So variable selection is not something that you necessarily are just going to do once. You might have to do it multiple times depending on whether there are outliers in your data set or you need to transform some of your predictors or transform your response in light of your regression diagnostics. So there's two aspects of variable selection that you need to think about when you're doing the variable selection process. So one is the criterion you use to compare the different models. So essentially this is your objective function. So how are we going to decide what is a good model and what is a bad model? The other aspect of the variable selection process is the strategy you use to search for the optimal model. In other words, what models am I actually going to consider in my analysis? So you can imagine a situation where I wanted to buy a car, for example. Okay, so I decide I need to buy a new van or something. So I want to buy a new car, and I might have different possibilities that I consider. So I might try the Honda Accord. I might try Honda Civic. I like Hondas quite a bit. Then we have Toyota Corolla. We have the Toyota Camry. Maybe I go with a Nissan Altima. We get some American cars in there, maybe the Ford Focus or the Ford Fusion. So I have these different cars I'm actually going to consider in my car buying process. There's some cars I may not consider at all. So for example, I may not consider a Ford F-150 because a truck won't work for my family. I may not consider a dump truck because that's not a very nice family vehicle. And so there are some cars that we're going to consider. There are going to be other cars that we don't consider. And so when we're talking about search strategy, we're talking about which models do we actually consider in our analysis. So maybe to be more specific in this particular process, maybe we have, let's say we have 4 predictors, or 4 regressors, x1, x2, x3, and x4. Well, I might consider the model that has x1, the model that just has x2, the model that just has x3, the model that just has x4, and then I might consider x1 and x2, x1 and x3, x1, x4, and then I have x1, x2, x3, and x4. So these are the regressors I'm using in these different models. And what you can see here is I actually am not going to consider all possible combinations. So there might be reasons for doing that. So in this situation, actually, I probably would do an exhaustive analysis. I would look at all possible combinations because there really aren't too many to consider. But if I had, for example, 500 different regressors to consider, then there'd be too many to do an exhaustive selection. And so the search strategy algorithm is how do I decide which models to even consider in my model selection process? So the first thing we're going to talk about is selection criteria. So how do we decide which variables should be in our regression model? So the most basic one is to use p-values. P-values are nice because they're usually default output when we are fitting our regression models. And the selection criteria that most people use is that they'll say that we should, after fitting a model with all the predictors or all the regressors, we're going to keep the regressors that have a p-value that's less than some threshold alpha crit. And you might set this alpha crit threshold to be something like 0.05, but because we have a lot of regressors, we might actually set it to be something higher. So oftentimes, alpha crit is something like 0.1 or 0.15. And any regressor that has a p-value less than that, we're going to keep in our regression model. So that would be our variable selection process. Another more popular method for deciding between models is to use some sort of information criteria. So there's many different information criteria that people use to decide between models. 2 of the most common are Akaiki's information criterion, AIC, and the Bayesian information criterion, BIC. And essentially what information criteria intend to do is they try to evaluate in some sense how well does the model fit the data, and then how complex is the model. And all the information criteria that I'm familiar with quantify the model fit using the likelihood function, the log likelihood function of the observed data. And so you guys may remember maximum likelihood estimation from a mathematical statistics course. The idea is that we estimate the parameters of our model with the values that are most likely to have produced the observed data. So after doing that, we plug those values in, our parameter estimates, into our likelihood function, and that gives us our estimated likelihood for that particular model, which we're going to denote here by m. So the script m here is going to denote a specific model that is under consideration. So we compute the log likelihood function for the model under consideration using the maximum likelihood estimates. Then we multiply that by -2. And this is a scaling thing that people do. But as you can see here, this part, this minus twice the log likelihood part, is a part that measures how well our model fits the observed data. And then, of course, the complexity of our model might be approximated or evaluated by the number of regression coefficients that are in the model. So here, P with a script m is going to be the number of regression coefficients in our model. So it's going to be, typically this is the number of regressors plus 1, where that 1 corresponds to the intercept. Or if you're including the intercept in your regressors, then it's just the total number of regressors, depending on how you look at that. And so this first part of this information criterion, we have minus twice the log likelihood, measuring how well the model fits the data, plus 2 times the number of regression coefficients. And so essentially what this is doing here is it's penalizing the model fit by how many parameters, how many regression coefficients are in my particular model. So I can get a really great fitting model if I add enough regressors to my model, but in doing so, I'm going to increase the penalty in my information criterion. And so these information criteria, they try to balance the two competing interests of keeping a simple model while also choosing a model that fits the data very well. And one of the main differences in information criteria is how we penalize the different models. So most of them start off with minus twice the log likelihood, but then the AIC information criterion multiplies the number of regression coefficients by 2, whereas the BIC criterion multiplies the number of regression coefficients by log n. And if you compare log n to the number 2 for most values of n, for the values of n we typically see with our data sets, log n is going to be more than 2, and so the Bayesian information criterion actually penalizes complex models more heavily than the AIC criterion, which means that the BIC criterion actually generally leads to simpler models. Okay, so that's the big picture. So we're looking at a balance between how well the model fits and then the complexity of our model. But some of you might be thinking, well, how in the world am I going to calculate the log likelihood of my model? That seems really complicated. And it can be in many different contexts. But for linear regression models, it's actually fairly straightforward. Minus twice the log likelihood is actually n, the number of observations in our data set, multiplied by the natural log of the residual sums of squares for that model divided by the sample size, plus c, where c is some constant that only depends on our observed data. It doesn't have anything to do with the fitted model. And what's interesting about this constant is actually, because it doesn't depend on the model, it's constant for every single data set, which means that when I'm computing the information criterion for different models, this c part is not in any way going to be a determining factor in my results, because it's going to be the exact same number for all the different models. So practically speaking, I can simply compute this part and then not worry about this constant part when I'm computing minus twice the log likelihood of my model. So because we're multiplying our log likelihood by -2, we actually favor models that have smaller AIC or BIC, because the smaller this number is, it means the better fit the model is, though of course we have this penalty term. And so what we really want is a model that fits the best while not being penalized too much for model complexity. So we prefer the models, so if we're comparing different models, we prefer the model that has a smaller AIC or BIC or whatever information criterion that we're using. Another criterion that people use is the adjusted R-squared value, which looks like R-squared with a little subscript of A, where the A stands for adjusted. It's another popular fit, I think, for a couple of reasons. So one is it's really easy to compute. It's also familiar to us because we have been working with R squared, the coefficient of determination, since the very beginning of the course. And lastly, it measures predictive value in some way, which is oftentimes something that we're interested in when we're doing our analysis. So you might think, well, why not just use R squared? We've already learned about that, so why not just use the original R squared instead of the adjusted R squared? So we've talked about this before in class, but in fact, R squared essentially will never go down as you add new regressors to your model. So even if I make up a regressor and then I add it to an existing model, almost invariably, I'm actually going to increase the R squared value. It's possible that technically the R squared value will remain the same, but more often than not, that R squared value is going to increase, meaning that based on that criterion is actually a better model, which is definitely not the case. We don't want to be adding useless, nonsensical regressors to our model. And so what the adjusted R squared does is it takes the original R squared value and then it penalizes it by the number of parameters. So here's the formula. There's different ways that you can compute the adjusted R squared. And we have 1 minus some number times 1 minus R squared. And you can imagine that if this was 1, right, if this constant right here was 1, or it's not really a constant, but if this factor here, this multiplicative factor was 1, then we would just get back the original R squared. And what's going to happen here is that we're actually going to penalize our model by the number of regression coefficients that are in our model. So essentially what that means is that just adding a new regressor by itself is not going to lead to an increase in the adjusted R squared. The adjusted R squared is only going to up if the new regressor actually has predictive utility in our particular model. And that makes it a much better choice for a selection criterion than the typical coefficient of determination. So what this means in summary, though, is that we're going to favor regression models that have a larger adjusted R squared. So if we have two regression models and one has a larger adjusted R squared, we prefer the one with a larger adjusted R squared. The next selection criterion that we're going to talk about is Malo's CP statistic. And this statistic is trying to get at the predictive usefulness of a model by estimating something known as the standardized total mean square prediction error. And it's looking at the mean square prediction error of each of our fitted values. So the mean or expected value of the square difference or prediction error between our fitted value and the expected true response for observation I. So this right here is the mean square prediction error, and because we're going to sum over all the observations in our data set, we have the total mean square prediction error, and then we standardize it by 1 over sigma squared. And you may recall that the mean square error of an estimator is the variance of the estimator plus the squared bias of the estimator in terms of trying to estimate the estimand, which in this case is the expected value of y sub I. So we're trying to compute this or estimate the standardized total mean square prediction error, but you might notice that this has several quantities, or at least a couple of quantities, that we don't actually know. So one of them is 1 over sigma squared. We don't know the true error variance for the errors in our model, and we don't know the true mean response for any of the observations, let alone for observation I specifically. So this is a bit of an issue. So we're going to have to estimate the standardized total mean square prediction error. And the way that we're going to do that for a model script M with PM regression coefficients, and I want to be very clear here, I say PM regression coefficients. So it's not the model that has P predictors or P regression coefficients, or P regressors, unless you're including the intercept in that. But it's a model that has PM regression coefficients. So that's the intercept, and then the first predictor, the second predictor, all the way to the last predictor in your model. So there's PM total regression coefficients in your model. And for a specific model M, with that many regression coefficients for a specific set of regressors, the way that we're going to estimate the standardized total mean square error is by taking the residual sums of squares for that specific model, dividing by the estimated error variance of the model that has all regressors that you're considering, plus 2 times the number of regression coefficients, minus n, the number of observations. And these quantities are all very easy to obtain. So once we fit a model, it's very easy to compute the Malo CP statistic for that particular model. And because we're trying to quantify a measure of total mean square prediction error, it makes sense that in general, we would want the CP statistic to be smaller rather than larger. But of course, there are some other considerations we should talk about. So one of the considerations is that for the model that has all regressors, so model big omega, the model that has every single regressor that we're considering in our model selection situation, the CP statistic is always going to equal the number of regression coefficients in your model. It doesn't matter whether this is a good model or a bad model. And so really, the CP statistic for the full model doesn't really tell us anything about its predictive usefulness. If you have a model with PM regression coefficients, and it fits the data well and has little or no bias, then we would expect the CP statistic to be about equal to the number of regression coefficients in your model. So one way of using the Malo CP statistic to identify a good model in your model selection search is to find models where the CP statistic is close to P. One of the things that the CP statistic is useful for is determining whether there's a biased fit, so whether we're having a problem with biased predictions. And if we do have a problem with bias in our model, then our CP statistic is going to be much larger than the number of regression coefficients in our model. However, at least in one of the books I was looking at, if you have a CP statistic that's less than the number of regression coefficients, that's not evidence of a bias. So if the CP statistic is less than P, that's okay. That's not something to be concerned about. But if we have CP statistics much larger than the number of regression coefficients in that model, then that's evidence of a bias in your model, and it may be wise to steer away from that model. And because we have this relationship where we're looking for models where the CP statistic is close to P, it's actually very common to plot the CP statistics versus the number of regression coefficients in the models, and then compare this to a 45-degree line, which is where CP equals P. And so essentially what we're going to do is we're going to look for models where the CP statistic is close to the regression line. And in general, because we want to minimize our total mean square prediction error, our standardized total mean square prediction error, in general, we favor models with small p and CP statistic. So we want simpler models. We want the simplest model that adequately explains the data. And so if a model has small p and the CP statistic is close to p, then that's evidence of a model that's relatively simple, but still has useful predictive power. And so essentially what we're going to do is we're going to look for values of CP where the CP statistic is close to the 45-degree line. One thing I do want to mention, though, is that some people say, because we're trying to quantify this total mean square prediction error, we really want the model that has the smallest CP statistic, regardless of how close it is to the line. But the predictions might be highly biased. So it's actually possible that you get a situation where you get a small CP statistic, but it's still well above the line. And because your predictions may be highly biased, I don't personally recommend this. I think the more standard procedure is to find, in general, the model with the smallest p where CP is close to PM. And just so you can get an idea of the kind of plot that you might expect to see, I'm going to go over to OneNote here where I've drawn a quick picture. So this might be a model that you look at. Here's the 45-degree line here, and you see the CP statistics. And in this case, this model right here has a CP statistic that's close to the line. It has a relatively small CP statistic, so that's a good thing. So you might favor this model perhaps, or because this one has a smaller CP statistic than this one and doesn't appear to suffer from bias, then it's possible you might actually prefer this one instead. Though in general, most people would say that you prefer the model with the CP statistic that's closest to this 45-degree line. So I think that most people would probably default to choosing this model right here for future inference. One thing I should also point out, though, is that if you had a choice maybe between this model right here and then this one right here, and both of these are pretty close to the regression line, you would still favor the model that has fewer regressors. And so because the number of regressors, the number of regression coefficients in this model right here is substantially lower than this model right here, even though both of them quantify, the CP statistic is close to this 45-degree line in both of the models, because this is the simpler model, we would favor this model for its simplicity. So another error criterion that people use to decide between models is the mean squared error, MSE, which what we do is we take the average of the sum of the square difference between our observed data and our fitted values. And this is a way of quantifying the amount of prediction error in our model. And unsurprisingly, we favor models that have a smaller mean square prediction error. Though, of course, you have to be very careful with your search algorithm because the more regressors you add, the lower your MSE is going to be in general. So you actually need a smart search strategy if you're comparing MSE. The root mean squared error is just the square root of the MSE, and this is another statistic that's oftentimes computed. There's a one-to-one relationship between them, and both give you essentially the same amount of information. So now I'm going to talk about cross-validation, and sometimes I go back and forth about whether this should be considered a search strategy or an error criterion, but I'm going to leave it in, at least right now, I'm going to leave it in the error criterion section, and here's the reason why. So, well, actually, we'll get to that. So what is cross-validation? So cross-validation is a way of taking your data, you break it into a training data set and a test data set. And then what you do is you use the training data set, you fit the model to the training data set, and then you make predictions for the test data set. And then you compute something like the mean square error or the root mean squared error or some other measure of prediction accuracy. And the idea is that you want, you're going to favor a model that has a smaller mean square error or root mean square error when you're using cross-validation. And so by itself, cross-validation is not an error criterion because it doesn't actually compute anything. So all cross-validation does is it breaks the data set into different parts and uses the training data to make predictions for the test data. But it's never used in isolation from itself. It's always used with some sort of error criterion. And so essentially, when you use cross-validation, you're computing something like the mean square error, but you're doing it in a way so that you don't overfit the model. And so I'm going to leave it in the error criterion section just because it can't be unlinked from the error criterion you use when you do the cross-validation. And it's not exactly a search strategy because all cross-validation does is consider a specific model, and it does cross-validation for that specific model. So you still have to do something else to decide which models you're going to consider and apply your cross-validation algorithm to. So just to do a very simple example where you wouldn't actually do it like this, but say you had data like this, okay? If you were doing cross-validation, you might break the data set into 3 parts. You would not do it this way, but we'll do it this way for simplicity. So this is data set, or data part 1, data part 2, and data part 3. And so what we would do is we would hold out, for example, the first set of data. We would use this section of data to fit our model, and then from that fitted model, we would make predictions for the first set of data. And then we would do the same thing where we would hold out the second part of the data and use parts 1 and 3. So use parts 1 and 3 to fit our model and then make predictions in between. And then lastly, we would fit them all to the data parts 1 and 2 and then use the fitted model to make predictions for the test data in group 3. And then after all those predictions, we would compute something like the root mean square error, the mean squared error, and that would be our measure of predictive accuracy. So there's actually different ways, though, that you can do cross-validation. You wouldn't do it like this. You have some sort of random sampling method. So one of the most common ones is leave one out cross-validation, where you actually hold out each individual observation and then use the other n-1 observations as your training data set, and then use that to predict the holdout observation. And the nice thing about this is that we can use some of the same ideas that we use for computing the jackknife residuals in order to do this very efficiently and very quickly. So we actually do not need to fit n-1, or I'm sorry, we do not even need to fit in models. We can actually do this with fitting one model and then doing some special linear algebra calculations to get all of the leave one out predicted values. Sometimes instead of doing that, though, people use something called k-fold cross-validation, where essentially they randomly assign the data into k unique sets, and then they use k-1 sets to predict the last set, and then they iterate through all the different sets in order to get their cross-validation predictions. So there are actually other ways of doing cross-validation as well, but those are by far the most common. And when you're using cross-validation as your selection criterion, you're going to prefer the model in general that produces the lowest MSE or root mean square error. And I only say in general because you could technically choose a different error criterion, but if you're using the mean square error or the root mean square error in connection with cross-validation, then you're going to prefer the cross-validation model that has the smallest MSE or root mean square error. So let's talk now about search strategies. Okay, so there's a couple different strategies you could use. So one of the easiest ones is the exhaustive search if you don't have too many predictors or regressors in your model. And in that case, you literally consider all possible combinations of your regressors. So you choose one regressor, so you consider all the models with just one regressor, all the models that have two of the regressors, all the models that have three regressors, etc. Of course, this doesn't work if you have too many regressors, so you can only do it if you have, say, maybe less than 20 different regressors in your model. And what you may have noticed when you're looking at all these error criterion is that they pretty much all depend on the residual sums of squares. And so what's actually kind of neat is that because all those error criterion that we've at least talked about depend on the residual sums of squares, one of the ways we can simplify our search strategy is that for each value of PM, so for each number of regression coefficients in our model, we simply need to find the one model that minimizes the residual sums of squares. And whatever model that is, that's going to be the best model for the models that have PM regression coefficients. And so when we actually do our analysis, as we'll see when we actually walk through the data example, we're only going to look at the model that minimizes the residual sums of squares for that many regression coefficients. If exhaustive comparisons is going to take too long, then people use stepwise selection to iteratively build models. And there's three kinds of models that people talk about. So one is backward selection. So backward selection starts with a full model, so the model that has all the regressors, and then it prunes the model one regressor at a time until under the assumption that as we remove regressors, the error criterion is actually improving. So once it's no longer improving, then we stop removing the regressors, and so we stop our model. So basically the idea is that we start with all the regressors and we keep removing them as long as it improves the error criterion. If we have too many regressors, however, that may not be feasible, and so a different approach is forward selection, where you start with the model that only has an intercept, and then you add regressors one at a time until the error criterion no longer improves. So as long as we can improve the error criterion by adding a single regressor, we're going to do so. And then you have both forward selection and backward selection combined, which is often known as stepwise selection. And the idea is that usually you start with all the regressors, you start removing regressors, but then at each step, we can actually consider adding a regressor back into the model if it's going to make an improvement. And this may seem like it shouldn't happen ever, because with backward selection, we're removing regressors to improve our prediction. But depending on the order you remove predictors or you remove regressors from your model, it might actually be possible that you removed a regressor early on in your process, but then at a later time, adding it back into the model actually improves the error criterion. And so the benefit of these approaches is that you're not considering nearly as many models, and so it's much faster to implement if you want to do it that way. So some other notes about model selection. So if you're using the p-value criterion to do your model selection, you shouldn't take your p-values too seriously. So we know that even if there's no relationship between the response and a particular regressor, just because of random variation, you can see effects that aren't really there in the population. And so, long story short, don't take your p-values too seriously. So you might be using them to choose your model, but don't think of them as actually measuring the strength of the evidence that regressor should be kept in your model. Another thing to think about is that stepwise selection tends to produce simpler models than are best for prediction. So oftentimes, if you want to do a prediction, then if you use stepwise selection, that's not going to be the optimal way of building the model. So some of these other selection strategies are actually better for producing a model that is focused on prediction. Lastly, you want to think about model hierarchy. This is a difficult thing for students to think about. But basically what this means is that if you're going to include complicated interaction terms or higher order terms in your models, then you need to include the simpler terms as well. And so one of the simplest examples is that if we fit a quadratic model with a predictor x and then a regressor x squared, let's say that x was not significant, but x squared was. Well, it wouldn't make sense to remove the predictor x while leaving the transformation x squared. Okay, because this would be a higher order polynomial term than x. And so if you want to include the x squared term in your model, you actually need to include the x variable as well. Another example that we might see is, so if we were fitting a model that was y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 x2 plus epsilon. So we're actually creating a regressor here that's a combination of x1 and x2. If this was significant and we wanted to keep x1, x2 in our model, we shouldn't remove x1 or x2. Technically, we can do that, right? Of course, we don't have to include all the regressors in our regression model. But if this interaction term is in our model, then philosophically, it makes sense to include x1 and x2 in your regression model as well. And in class, we'll actually go through a model selection example that I think will be very informative for everybody.